Hi, thanks for checking out our work on point cloud forecasting as a proxy for 4D occupancy forecasting. For autonomous perception and navigation in the real world, traditional methods rely on costly human annotation in the form of object tracks, labels, bounding boxes, and HD maps of cities, because of which they can be difficult to scale. In this work, we revisit a self-supervised task called point cloud forecasting, which does not require any annotations and is scalable. This task takes in a set of past lidar point clouds and attempts to forecast the future lidar point clouds. While this seems straightforward, understanding where a point will move in the future is non-trivial. Points depend on the intersection of rays from the lidar sensor and the environment. These rays change with change in sensor extrinsics, that is, the motion of an autonomous vehicle, and sensor intrinsics, that is, the ray sampling pattern. Therefore, accurately forecasting points requires accurately forecasting these sensor parameters. But we argue that autonomous systems should make predictions about their environment and not their lidar sensor. This is reasonable as sensor extrinsics are available as part of the future motion plan, and sensor intrinsics are available from calibration. To this end, instead of directly learning to forecast points, we propose to learn and forecast an intermediate volumetric representation that resembles occupancy, which can be learned from the same training data as point cloud forecasting. We call this task 4D occupancy forecasting. Given this future spacetime occupancy, one can render future point clouds using differentiable volumetric rendering. On adopting this occupancy-first approach, we dramatically improve the performance on point cloud forecasting as compared to the state-of-the-art. We also propose to change the benchmarking protocol of point cloud forecasting, aka 4D occupancy forecasting. The widely used chamfer distance metric does not directly evaluate the spacetime geometry of the scene, as it does not assume any correlation between points. We instead find that querying rays into any future scene representation and obtaining the distance traveled by these rays is a better physical quantity for evaluating the underlying spacetime geometry. Using this distance traveled by the ray, or depth, one can compute the L1 and absolute relative errors with the ground truth ray depth. This ray-based quantitative analysis shows that we significantly improve the performance on point cloud forecasting as compared to the state-of-the-art, and for completeness, we also evaluate with the standard chamfer distance metric used by prior work in the main paper. Because we factor out sensor parameters from the task, the intermediate spacetime occupancy can be used to simulate different lidar sensors by changing the intrinsics. Here we show a single 4D spacetime occupancy volume rendered with 3 different types of lidar sensors. We quantitatively test for this zero-shot cross-sensor generalization by training our method on Argoverse 2 and testing it on kidiodometry. Surprisingly, this model beats the state-of-the-art on kidiodometry by a large margin. The 4D occupancy can also be used for novel view synthesis by changing the extrinsics. Here we show dense depth maps rendered from the occupancy volume along a new trajectory of the ego vehicle. To summarize, we propose to factorize sensor parameters from the task of point cloud forecasting, thus focusing solely on 4D occupancy forecasting. This helps us in learning a low-level and highly generic representation. Evaluating this representation requires a ray-based querying protocol so that methods can be evaluated for their forecasted geometry rather than a set of points. Thank you for listening.